Water. This simple substance, perhaps humanity's most precious resource, is what distinguishes our planet, Earth, the blue planet, from other planets in our solar system.
Hi, my name is Deepika Kurup and my project is titled Novel Photocatalytic Composites for Degrading Organics and Inactivating Bacteria in Wastewater. Now every summer my family and I travel across the world to visit relatives in India, a country infamous for its hot summers. Now my family was always very careful to make sure that the water we drank was safe. However, I soon realized that not everyone was fortunate enough to enjoy the clean water we did. Outside in the busy streets of India, I could see children filling up plastic bottles with dirty water from the roadside. Watching these children forced to drink water that I felt was too dirty to touch changed my perspective on the world. This unacceptable social injustice compelled me to find a solution to the world's clean water problem. So I started doing some research, and I learned that we are facing a global water crisis. According to the World Health Organization, 780 million people in the world lack access to clean drinking water. The National Academy of Engineering lists providing access to clean water across the globe as one of the 14 grand challenges we must overcome in order to better our society in the coming century. Now currently in many developing countries, solar water disinfection, or SODIS, is used as a cost-effective means of purifying water. Now SODIS is energy efficient because it only uses solar energy for purification. Basically, the DNA of the harmful pathogens is destroyed by the powerful UV radiation coming from the sun. This eventually rids the water of all pathogens. However, the SODIS process is often very slow. So recently, a method called photocatalytic solar disinfection has been used to accelerate the SODIS process. When UV radiation strikes a photocatalyst, such as titanium dioxide, or TiO2, an electron is energized from the valence band to the conduction band, and this leaves a positive hole behind. These electrons and holes combine with oxygen and water to create reactive oxygen species, such as superoxides, hydrogen peroxide, and hydroxyl radicals. These reactive oxygen species are responsible for destroying bacteria and degrading organics in water. But there are several disadvantages to current photocatalytic solar disinfection methods. See, typically the photocatalyst is coated on the inside of a clear plastic bottle, but that actually blocks some of the UV radiation and diminishes photocatalysis. Also, these coatings are not tightly bound to the plastic bottle, which means they wash off into the water and people end up drinking the photocatalyst. In 2012, I began my journey as a scientific researcher with the goal of overcoming these disadvantages of current treatment methods. And I created my first photocatalytic composite for water purification. My composite had two photocatalysts, titanium dioxide, or TiO2, and zinc oxide, ZNO. I also used cement as a binding agent, so the composite would not wash off into the water. I converted my deck, garage, and basement into a makeshift laboratory and began synthesizing my composite and testing for bacterial inactivation and organic degradation. For bacterial inactivation, I collected water from the Nashua wastewater treatment facility. And for organic degradation, I used an organic indicator dye called methylene blue, which turns from blue to clear when it's oxidized. I also built several different prototypes with my composite, such as a rod that could easily be placed inside water bottles and photocatalytic spheres. I also built a photocatalytic water purification panel. Now this panel is constructed out of 4 PETG tubes, each with about 30 photocatalytic spheres, and a parabolic trough reflector to concentrate solar energy along the entire length of the tube. I entered this project in the 2012 Discovery Education 3M Young Scientist Challenge, where I was honored to win the grand prize and title of America's Top Young Scientist. Now the following year, in 2013, I created a UV-Vis photocatalytic system that could purify water in UV light, visible light, and even in the dark. I hypothesized that doping my photocatalytic composite with silver would enhance the bactericidal effects of current photocatalytic solar disinfection methods. So I developed simple, fast, and cost-effective methodologies to synthesize lightweight photocatalytic composites for water purification. I'm also the sole author on a published pending patent on this method. Again, I collected water from the Natural Wastewater Treatment Facility, and I tested for both Enterobacteriaceae and aerobic bacteria removal. The silver-doped photocatalytic composite was able to inactivate bacteria in sunlight, visible light, and in the dark. The enhanced bactericidal properties of the AgTi2ZNO composite can be explained by 3 different mechanisms. Doping with silver introduces an intermediate band gap and allows absorption in the visible light spectrum. Silver also prevents electron-hole recombination, which results in the generation of more reactive oxygen species. And finally, silver has inherent bactericidal properties, and it binds to and alters the DNA of pathogens, disrupts their cell membrane, and deactivates enzymes. I submitted this project to the 2013 Stockholm Junior Water Prize competition, where I was honored to be first place in New Hampshire, as well as runner-up in the nation. Now, in order to further enhance the efficiency of water purification and for easy deployment, in 2014 I developed silver-doped Pervious composites for water purification. Now, to synthesize these composites, I adapted design principles from Pervious concrete. Immediately after filtration, the plain Pervious composite showed only a 20% reduction in total coliform bacteria, while the photocatalytic Pervious composite produced 98% of total coliform. Exposure to sunlight inside beakers containing composite discs resulted in 100% inactivation of total coliform by the plain Pervious composite in 3 hours, and the photocatalytic composite in just 15 minutes. I submitted this project to the 2014 Stockholm Junior Water Prize, where I was honored to be first place in the nation and represented the United States at the international competition held in Stockholm, Sweden. My composite also has several diverse applications, such as use in water tanks for long-term storage and in point-of-use water purification systems, like this photocatalytic filter I created. Also, my composite does not produce any toxic byproducts, and theoretically it can be used forever because it's a catalyst and does not get used up in the reaction. Over the past 3 years, conducting scientific research has opened up many incredible opportunities for me. I was honored to discuss my project with President Obama, present at the White House Science Fair, meet Crown Princess Victoria of Sweden, and dine with Swedish royalty in Stockholm City Hall. I've met celebrity scientists and environmental activists like Bill Nye the Science Guy, Don Henley of the Eagles, and Oscar-winning actor Robert Redford. I was also humbled to receive the 2014 President's Environmental Youth Award from the U.S. Environmental Protection Agency and White House Council of Environmental Quality. And most recently, I was named one of Forbes' 2015 30 Under 30 in Energy. My project has taught me that raising awareness is also imperative in solving global challenges, and I've spoken at schools across the globe and at conferences and events, such as the OU International Water Conference and 2 TEDx events. In my journey to help solve the global water crisis, I've learned that only when many minds come together and are set on achieving a single goal is it possible to tackle global challenges. It's imperative that engineers, scientists, policymakers, industrial leaders, and the general population all work together to find joint solutions and increase awareness for the global water crisis. Water is something we all need to survive, and for that reason, we all share the responsibility of making access to clean water available across the globe. Thank you for watching my video and considering me for the 2015 Davidson Fellow Scholarship.